So when we were practicing the previous time, I told you that for some of the ions, and they may come from the transition elements part or some other elements from the periodic table, in which you cannot predict the charges on them. Yeah, you are able to predict the charges on group 1, 2, 3, 5, 6, and 7. But what if it does not belong to any of these groups? Since
Mm.
group 4 is not a part of it, in group 4, we have a few ionic compounds. You'll see that lead Pb can form a +2 ion. So how would you get to know that? You can get to know that from the name of the substance. They actually give you the name as a hint. Now let's take a look. Sometimes the names are given like this: lead 2 oxide. This means on lead, the symbol for which is Pb, there would be a +2 charge. Iron 3 chloride, it tells you that iron has a +3 charge. Copper 2 sulfate, it tells you copper has a +2 charge. So
Yeah.
actually that is pretty easy to work out that way, because every time they are using a metal, they are writing its oxidation state or its charge right next to it in Roman numerals. So what we do is that we go with for the most common ones that we use in IGCSE chemistry. So for the positive ones, we're gonna use zinc, silver, hydrogen, ammonium, and these are the charges on this one. It's better that you should learn these since that's clearly mentioned over here. So you must memorize these, right? For the negative
Yeah.
ones, we have polyatomic ions. When I use the word polyatomic, we're also going to use the words group ions. When I use the word group ions or polyatomic ions, it literally means that the ion is made up of multiple atoms. Poly means many, and atomic means atoms. Take a look. This one is made up of 5 atoms: one nitrogen atom, 4 hydrogen atoms. This one is made up of 4 atoms: one nitrogen, 3 hydrogen, 3 oxygen, sorry. This one is made up of 2 atoms, one oxygen, one hydrogen. This one is made up of four, one carbon, 3 oxygen. This one is made up of five, one sulfur, 5 oxygen. So these are all polyatomic ions. We also call them group ions, since
Mm.
they are composed of not a single element but a group. You'll see this is a single element, single element, single element, but these are multiple elements.
Yeah.
How do you know one is a single element or multiple? If there is only one capital letter, one element. Two capital letters or multiple capital letters, more than two maybe, it's a group
Mm.
ion. It's a
Yep.
polyatomic ion.
Yep. Okay.
All right. We are supposed to memorize these ions with their names along with their charges and formulae. So this
Okay.
entire table 7.2 is to be memorized by the student.
Yep.
All right.
Okay.
Moving on, sometimes we have confused endings. Now, confused endings are the one in which we have similar number but a different charge on both ends. What do? We actually simplify them. We don't write Cu2S2. I hope you remember I taught you the
Yeah.
previous
Yeah.
time. We
So it will be
simplify it
C.
to
Yeah.
Cus. Right, right. Now you
Yeah.
know. So it won't have a problem.
Mm.
One thing. Second thing, do not confuse ions such as sulfate and sulfide. Now, sulfate means SO4 negative 2 and it's a group ion. Sulfide means just the sulfur ion and it's also negative 2 by the way. This one is
Mm.
sulfide, just the sulfur atom which is shown with a yellow ball, and this one is sulfate in which a yellow ball is right in between and there are four red balls representing each of the oxygen atoms as you can see in the formula.
Yeah.
All right. So
Yeah.
what do? There is another way of knowing from the name. Okay. Now he has been using some bold letters in there. Take a look. 8 has been bolded. Ide has been bolded. Any ide ending means that there isn't anything complicated or made up of multiple atoms. Any 8 ending means it definitely has a polyatomic ion or
Mm-hmm.
it has a group ion involved. So ATE in the name represents a group ion involved. ID in E in the name represents it does not have a group ion. So that's another way to look at it.
Yeah.
Apart from the fact that we simplify the numbers, this is another piece of information that the student must remember. So memorize this. IDE at the end, suffix means the last part of the name. IDE means probably a single atom. ATE means a groupine. It will have multiple atoms, right? So let's
Mm.
just move forward and deducing the formula for an ionic compound. Now we have already tried this and you already know this is going to be like this, right? For example, if you're given sodium and you're given oxide, you obviously know that we're gonna work it like this over here, this over here. This is gonna become Na2O1, and finally, this is gonna become Na2O. So you already know how to work this out.
Yep.
We've practiced it a lot, but so far, example number one is easier. We only practice it with single atoms. We never practice anything with multiple atoms. So that's what we're gonna do with example two. Now, in case of example 2, take a look. One of the ions is based on a single atom, but the other ion is a group ion. Now, it has
Mm.
multiple atoms. When that happens, whenever group ion has multiple numbers, we always add bracket to them before writing the number in the subscript. For example, let's take a look. This one is Ba2 plus as given over here. This one is actually negative. So when we're going to take this negative 1 over here and this positive 2 over here, what do we do?
Yeah.
We can write 1 over here, but we're never going to write it like this. This becomes 32. It's also mentioned in the key point over here.
Mm.
That doesn't work that way. So what do we do? We don't write this 2. Instead, we put up a bracket first and then write 2 after the brackets or outside the brackets to be more precise. This
Yeah.
tell you this there are a whole of 2 of these ions. This 2 means it's usually read as twice, means you're gonna read it. We're gonna simplify it to this form BaNO3 like this. So how do we read it? We read it BaNO3 twice. We don't read it two. Two becomes twice, three becomes thrice. If
Mm.
the two
Okay.
or three is written after the brackets, whenever you're gonna read it out loud, you're
Yeah.
not gonna read it like two. You're gonna say twice. You're gonna say thrice. This way, whenever you say twice or thrice, the other person who is hearing it would automatically understand that there is a bracket involved or
Mm.
there is a group ion involved. That's why you're using the terms twice or thrice instead of two or three. All right. Let's
Yeah.
do another example like this one. Now, we have iron 3 and we have the same polyatomic ion nitrate. How are you going
Yeah.
to work it out? And I'm also going to turn the annotations on for you. It's up to you whether you say it out loud or whether you annotate it on my screen.
Yeah. Yeah. Sure. Let me just solve it and I'll do it.
Sure, take your time.
Sir, I'm not getting it.
All right. This is -1, so I'm going to take it all the way to here. This is +3. I'm going to take it all the way over here. So when I am about to write this one, I'll write this one over here. But when I'm about to write this 3, I'm going to put up a bracket first and then write this 3 after. Simplifying, we don't never write 1, so it's going to become FeNO3 price. That's about it. So we're going to
Okay.
say it out loud, FeNO3 price. Make sense? Let's
Yeah.
practice more questions. That way you're going to get confident about these. Okay, let's practice something different. Okay, we have aluminum. We have practiced aluminum a lot before, and we have carbonate, and this is 2 minus. Okay, go ahead.
Okay. Yeah, I'm done.
All right, go ahead.
So first, it'll be aluminium Al,
Al. All right.
2,
2, great.
then CO,
CO,
3,
3.
and then again 3.
What about the bracket?
Oh yeah, bracket and then 3.
Brackets and then 3. Now that's fine. That's correct. If you have brackets right there and brackets with C and O, then that's correct. That's
Hmm.
perfectly all right.
Okay.
Okay, let's try another one. Let's use the same ion, Al plus 3. This time I am intentionally giving you a confused ending, having the
Okay.
same charges.
Is it that they both will get simplified, so only 4 will be left out, right?
Exactly.
Yeah.
Good.
Okay.
Very good. So your answer comes out to be
I'll get the direct answer? I want to, or I should say the steps.
No, no, just the answer, that direct
Okay,
answer.
so Al
Al
bracket PO
bracket PO.
bracket
Okay, bracket.
4.
Actually, 4 stays inside. 4 was previously a part of it. So 4 stays inside the bracket. And we do not need a bracket if there's just one polyatomic ion. There's just one group ion. We only need brackets if we have a bigger number like 3, 3, and 2. So if we don't have a bigger number, it stays like this. So that's your answer right there, without any brackets. We do
Okay.
not put brackets if the number outside is just one, right?
Yeah.
Good, good. So now you know. Let's move on. Okay. The same thing has been explained over here. Ferrocene sulfate. You know, how do we move these? Now, this is the point where the book tells you the movement of numbers
Mm.
and to put the brackets along with it. Right? So I've given you the same rule a lot before, like 4 or 5 pages before this page. So that helps the students. They're doing the same thing with CnCl2. They're doing the same thing with simplifications. You already know how to simplify. You know that we never
Mm.
write Ca2O2. Instead, we write CaO, which is written over here. Okay. So
Yeah.
you know everything about it. Let's move on to the point there, which we actually need to study and haven't studied before. This is giant ionic structures. Now, all ionic compounds form crystals. Crystals means they at room temperature are solid. Crystal
Mm.
means that they have specific shape. Now these crystals are known as lattices. Why do we use the word lattice? Actually, lattice is the positive and negative ion packed together in a regular way. So it's actually like a regular array. When I use the word array, it means something arranged like this. So what we are talking about over here is that in case of NaCl, and I'm gonna
Mm.
go with a little bigger diagram.
Yeah.
So in case of NaCl, we have Na positive, and then we have Cl negative, and then we have Na positive again, and then we have Cl negative again. So they are in alternate arrangement, positive, negative, like that. So
So
much
then
so
there will be attraction, right?
there would be attraction. That's the point. So if
Mm.
every positive is surrounded by a negative and every negative is surrounded by a positive, you would know that they are getting attracted towards each other by strong electrostatic forces of attraction. And when I use
Yeah.
the word electrostatic, it means a positive is attracting a negative or a negative is attracting a positive. And the structure is repeated throughout. This is a gigantic structure with billions and trillions of ions arranged in a similar manner. Hence, we use the word lattice. Lattice
That.
represents this exact structure. Lattice represent that they are tightly packed. Lattice represents they have alternate arrangements, negatives and positives. Lattice represents that they have strong forces of attraction in between themselves. Lattice means that this is a network structure, three-dimensional again. So much
Mm.
so that you can show it like this in the form of drawing and actually a model like this. And this model exactly tells you blue ball, green ball, blue ball, green ball, blue ball, green ball, and this repeats no matter if you go from left to right or right to left, top to bottom, bottom to top, whichever side you're going to move to, you're going to find the same alternate arrangement. All right.
Yeah.
So that every time a positive is actually surrounded by a negative, or negative is surrounded by a positive. Now,
Okay.
in
So
these diagrams, all right, go ahead with the
how
question.
how do they ask the question from this one?
Yeah, that I'm going to explain. We are going
Yeah.
to explain how the questions are asked usually in this portion. So, in
Mm.
order to explain these structures, these diagrams, the ions are usually drawn in an exploded view. In exploded view, we try to push the ions a little bit away so that you can actually understand what's happening in between them. Ball
Mm.
and stick models like this one are pretty common. Students usually make them on their own. They take balls and then they take plastic sticks and they combine them with the help of gum or with the help of some glue, and they make models like this. If you
Yeah.
take a look at this model, every black ball is representing a sodium ion. Every green big ball is representing a chloride ion, and it clearly tells you that the sodium ion is smaller in size than the chloride ion. Understandable. We do understand chlorine is a bigger atom, so of course chloride ion would be bigger in size than the sodium atom. Moving on, in turn, each chloride ion is surrounded by six sodium ion, or each sodium ion is surrounded by six chloride ions. How? I'm going to pick the centermost sodium ion. Okay, since this is also black, so I'm gonna use a different color. I'm gonna pick this one, the exact sodium ion in the center. So how many chloride ions it is surrounded with? There is one chloride ion in front of it, one on its back, one on its right, one on its left, one on its top of it, and one at bottom of it. Six. Do you understand?
Yeah.
Okay. Let's assume manal is a positive ion. Then where would the negative ions lie? One would be in front of you, one would be at your back, one would be at your left, one would be at your right, one would be on top of you, and one would be at the bottom below you. That's how we complete six surrounded ions. So every sodium is surrounded by six chloride, and every chloride is surrounded by six sodium ions.
Okay.
That's how we explain it. And that's how we ask the questions from students. That usually in a lattice like sodium chloride, how
Hmm.
are the ions surrounding one another? Then you need to tell them the exact lines. Each sodium ion is surrounded by six chloride ions, and in turn, each chloride ion is surrounded by six sodium ions. That's how you're supposed to answer. And this pattern actually repeats itself throughout the structure.
Yep.
That's why we call it a lattice, right?
Yeah.
Moving on, we further describe this. The structure of sodium chloride is described as a giant ionic lattice. Lattice is the specific arrangement. Since this is made up of ions, we call it ionic. Since this has trillions and trillions, billions of atoms, maybe even more, we don't even have a word for it. So we use
Um.
the word giant. Giant is not here in the sense of big. Giant is here because it has so many ions and so many attractive forces. So there are no individual molecules. This structure, this lattice extends throughout the structure in all directions. There is no limit to number of particles present. All right. That's why we use the word giant.
Okay.
Okay. When you're gonna study covalent compounds, you understand why we use the word giant with it. Now we're gonna explain one more structure. That is the structure of magnesium oxide. Now, in case of magnesium oxide, MgO, it contains Mg positive two ions and oxide O negative two ions.
Mm.
It has exactly the same structure as sodium chloride. The only difference is that magnesium oxide lattice is held by stronger forces of attraction. The point you need to understand is that Na has a plus one and Cl has a minus one charge. So they
Mm.
have less strong forces of attraction as compared to something that has a plus two and a minus two charge. And again, even this one has lesser forces of attraction for something that has a plus three and a minus three charge. Get the point?
Yeah.
Higher the number, stronger the electrostatic forces of attraction.
Okay.
So this one would have the strongest, this one would have stronger, and this one in comparison has just strong forces of attraction. So among all of these, this one is going to be the strongest. Why? Because it has bigger charges, bigger numbers. Make sense?
Yeah.
Great. Moving on, the physical properties. Now we're going to state many physical properties and we're going to discuss the reasoning. This is the portion which is considered a lot in exams.
Oh, okay.
All right.
Mm.
They tend to either ask you to list the physical properties. Sometimes you need to mention two physical properties. Sometimes you need to mention three. Every paragraph has some starting italic words that this is the property. If they ask you to mention the property, this is fine enough. This is fine enough. The italic portion is fine enough. So the first property is ionic compounds have high melting and boiling points. The second property is ionic compounds tend to be crystalline, which means they are crystals, solid crystals, like this one. This crystal has a specific shape. That's why we use the word crystal.
Mm.
Now, they have high melting and boiling points because they have strong electrostatic forces of attraction. This is the reasoning. When they ask you why or how, then you're supposed to explain this reasoning. So a lot of energy has to be supplied to break the strong forces of attraction and then melt the substance or boil it. All right. So
Yeah.
that's why they have high melting and boiling points. For example, if I talk about NaCl, the simple table salt that we eat every day. If I talk about the melting point is 801 degrees centigrade, which is pretty high. If I talk about the boiling point, which is even higher, it's around 1465 degrees centigrade, which is pretty high as compared to water. Water has a melting point of 0 degrees centigrade, pretty low. Boiling point of 100 degrees centigrade, again, pretty low in comparison to this one. Since water is not an ionic compound, ionic compounds have pretty high melting and boiling points. A few
Yeah.
hundred in melting points, or maybe a few hundreds or thousands in case of boiling point. So, moving on, ionic compounds tend to be solid crystals. It actually reflects the regular arrangement of the ions in the lattice. The crystals are too small to be seen with naked eye. We can usually only see it with powerful microscopes. For example, magnesium oxide is white powder because individual crystals are too small to be seen with the naked eye. So
Yeah.
when we try to see it with the naked eye, it seems like a white powder. But when we use powerful microscope, it tells us magnesium oxide is cubic like this one, exactly like sodium chloride. All right. So these are two
Yeah.
properties in there. Remember, high melting and high boiling points cannot be two separate properties. This is just one property. The second one is ionic compounds tend to be crystalline. Let's move on to the next page for the further set of properties. So the third property in here is this one. They tend to be brittle. Fourth, they tend to be soluble in water. Fifth, they are insoluble in organic solvents. Now, starting with the third one, they tend to be brittle. Brittle means which breaks when reshaping is attempted with force.
Okay, so they can ask us the physical properties of
Ionic
ionic
compound,
substance or compound. So then
right?
we have to give the points with the reasoning, right?
No, just the points.
No, no need of the like the reasoning or something.
Reasoning is required when they don't ask you about the physical properties. Instead, they only tell you one physical property and they ask you why is that so or how is that possible. Then you are
Oh,
supposed to give the reasoning for that specific property. Remember, they're not going to ask you all the physical properties and their reasons because the question then would then be too big. You might require 6 to 7 lines to just explain
yeah, yeah,
reasons for two specific properties. So they don't tend to ask the question like this. They're going to give you 3 to 4 lines and they're going to ask you to write two properties of ionic compounds. Good enough, a small short question with 2 to 3 marks. Or they might discuss why ionic crystals are brittle. Then you need to explain this 2 to 3 line reasoning.
yeah,
Okay. So whenever they ask the reason, they usually discuss that specific physical property.
yeah.
Or they do
Mm.
not discuss physical properties at all, and they ask you to list them. So you are supposed to mention any two or any three, whatever the number the examiner asks for, usually they tend to ask 2 to 3 physical properties at a time,
Yeah. Okay.
right? So let's
Yeah.
come to the third physical properties. They are brittle. Brittle means they break when we try to reshape them. And reshaping is usually attempted with force. So when we try to put some force on them, even a small distortion in the crystal, what happens is that the charges or the layers move in such a way that negative confronts negative, positive confronts positive. When that happens,
They'll
instead
be.
of attraction, they
Yeah.
would start repelling. So this
Mm.
splits the crystal apart. The entire crystal breaks. We can't reshape them. Hence, we use the word brittle. Remember, we have discussed in the periodic table chapter that metals can be reshaped, they're malleable, you can convert them into sheets, they are ductile, you can actually stretch them into wires, but
Yeah.
that the same thing is not true for ionic compounds. If you're going to try to stretch them or if you're going to try to hammer them, the crystals are going to break instead of getting into a new shape. That's what the word brittle means. And there
Okay.
is a perfectly good reason behind it. Because whenever we try to apply some force instead of attractive forces, this results into repulsive forces, and repulsive forces break the whole crystal apart. All right. So,
Yeah.
next up is about solubility. They tend to be soluble in water and they do not dissolve in organic solvents. Organic solvents such as petrol, such as alcohol. These are the organic solvents mentioned. They have mentioned alcohol over here or petrol over here. These are organic solvents. So ionic compounds do not dissolve in organic solvents. However, they do dissolve in water. Means in everyday life, you might have seen that if we take a glass of water, we fill it up with water, we take a spoonful of salt, we throw the salt into the glass, it will settle down at the bottom first. And as soon as you start stirring the whole thing up,
Mm.
the salt will start to disappear. So ionic compounds or salts usually tend to dissolve in water. After a few minutes of stirring, the whole salt will dissolve into the water. So that means they're soluble in water and it would disappear, right?
Yeah.
The same thing is not going to happen with petrol or alcohol. If you throw a tablespoon full of salt in alcohol and if you try to dissolve it, it would simply sit at the bottom. No matter how long you're going to stir it, it won't dissolve in petrol or it won't dissolve in alcohol. All right. Now there is
Yeah.
some extensive explanation that how does it dissolve, but again, that's actually not a part of O levels. But I'm going to go for a little bit of explanation. This might help you with in A levels. This is not going to be good enough for O levels though. So ionic compounds actually have charges, positive and negative charges. They're soluble in water because water is a covalent molecule, which we're going to study next in the next chapter, chapter number 8. But sometimes the oxygen atoms or the hydrogen atoms have slight charges. Oxygen has a slightly negative and hydrogen has a slightly positive charge. We call these kind of molecules polar. If the molecules are polar, they will get attracted by the ionic compound. Seems a little bit difficult, but yeah, that's the reason they dissolve in water. And since hexane has no kind of charges, they cannot attract or break the ionic lattices.
Can you
Since
explain the reason of color again?
NaCl is actually made up of Na positive and Cl negative ions. Now they
Yeah.
have charges. Na has a positive charge, Cl has a negative charge. When I talk about water, this is the formula of water. Water tends to have a slight positive, not a complete, a slight positive charge on it in terms of hydrogen and a slight negative charge on oxygen. What happens is that these charges can attract the ions in NaCl. Of course, the oxygen is going to attract the sodium and the hydrogen is going to attract the chloride ions. Hence, they dissolve. They are soluble. When it comes to petrol, all right, NaCl has charges, petrol has no charges whatsoever. So there is nothing to attract or repel over here. In case
Mm.
of water, yeah, attractions are possible. This is going to attract this, and this one is going to attract this, right? But there
Yeah.
are no attractions possible over here. So they don't dissolve. So in this case, this specific one is insoluble. So actually, things like to attract or repel, they may dissolve into one another, but if there are no reasons for attractions or repulsions, they may not dissolve into one another at all. And the same
Yeah.
thing happens over here.
Mm.
Now, if you're not able to do this extension work, remember this extension work or most of the purple portions extension works in the book are usually as an introduction to A levels. They are not considered in your exam. All right.
Yeah.
Okay, moving on. Next and last property. Now, electrical conductivity is one of these properties, but they made a separate heading out of it so that they can explain the whole thing. Again, this is one of the properties, and you can always mention it. Now, electrical conductivity has been discussed separately because it's a little bit conditional. Now, ionic compounds do not conduct electricity when they are solid. They conduct electricity when they are molten, means we have melted them on their melting point,
Liquid.
or when they are dissolved in water, right? That's why we call it conditional. Now think about it. We have NaCl and we take some salt. I take some NaCl. I put a wire over here, and I connect it to a battery, and then I connect it to a bulb, all right? And then when I turn on the battery, the bulb does not lit in case of NaCl solid. Now, when I go for the melting point of 801 degrees centigrade, I heat it up, NaCl then becomes a liquid, right? Over this temperature, NaCl will be converted into a liquid. Let's take that liquid in a container. Let's suppose we have NaCl liquid over here, and we put the wires in it, and we connect it to a battery, and then we connect it to a bulb, right? Poorly drawn bulb, but definitely this bulb will light up. This means liquid NaCl is conducting electricity. This means liquid, or when they are molten, they do conduct electricity. There is another way when they can conduct electricity. Let's take some NaCl, dissolve it in water, and use the same container. Let's fill up some of the container with water. Let's throw in some NaCl, and we also have some NaCl in water. Again, put up the wires, connect them to our battery, then connect them to our bulb. All right, and again, this bulb is going to light up. So this is in this case, we call it aqueous solutions. Remember, the word aqueous itself literally means water. So aqueous solution means solution in water. So when NaCl is dissolved in water, the bulb lights up. It's a conductor. When it's molten to converted to be converted into a liquid, again the bulb lights up. But when it is in solid form, the bulb does not light up. We have proper reasoning for it. When they are in solid form, the ions are stuck in fixed position and are not free to move.
Mm.
When we melt it up, what happens is that we break these positive and negative ions apart, so much so this Na positive is free to move in the entire structure, so is this Cl negative. So they are not bonded or stuck to one another anymore. All right? Then they are
Yeah.
going to conduct electricity. Or when they are dissolved in water, the whole lattice breaks. All the Na positive and the Cl negative are able to flow in water freely, like all the positive and negative ions are swimming in the water separately. They're not stuck in a lattice. When they're free to move, they can carry the current, and then they conduct electricity. This is a little hard to explain in the form of words. We have many interactive YouTube videos about it. Just search the words electrical conductivity of ionic substances on YouTube. Go for an animation, not an explanation, an animation. and you will be able to see that the ions are stuck in a solid lattice. But when we melt them and when we dissolve them in water, they're free to move and swim around the water or throughout the place. So, yeah, they can carry the current, they can move here and there, hence they're conductors. But when they're stuck, they cannot carry the current from one place to another, so they do not conduct electricity. So, yeah, this is a property of ionic compounds, but this property is a little bit conditional. In one case, it's not a conductor. In two other cases, it is a conductor. In solid form, it's not a conductor, but in liquid molten form, or when dissolved in water, we usually call it aqueous solution, it actually becomes a conductor, and a very good one at that. All right.
Yeah.
So do try a YouTube video about it. I can
Yeah.
even share a link with you in terms of animations. And the
Yeah.
animations are gonna be real fun and explain the whole thing with the little beautiful drawings of positive ions of sodium and the negative ions of chloride, and you're gonna understand the whole thing instantly.
Mm.
Right? And
Yeah.
this completes our chapter.